Hello, my name is David Jaramillo, and my project is on amicable numbers and the primes. An amicable pair is two whole numbers, and when you sum the proper divisors of any of the numbers in the pair, you'll get the other number. An example of an amicable pair is 220 and 284. So when you sum the proper divisors of 220, for example, you will get 284 and vice versa. There is a deep connection between prime numbers and amicable numbers, in a way that amicable numbers have a standard prime representational form. This means that they can be represented by a specific pattern of prime factors. So essentially, the goal of this research is to uncover this connection and provide new knowledge and new understanding of amicable numbers. A standard prime representational form for amicable numbers was already attempted in the 9th century by David Ibn Qura. However, his form failed because it didn't account for all amicable pairs known. And as of this year, due to the multiple computational organizations and programs, there are 1.22 billion amicable pairs known. For this research, I will use perfect numbers. Perfect numbers are similar to amicable numbers in a sense that when you sum the proper divisors of a perfect number, an example of 1 is 6, you will get the same number. So in the case of 6, when you sum its proper divisors, 3 plus 2 plus 1, you will get the same number 6. So for perfect numbers, there is a already established prime representational form that was done by Euclid and Euler, and it is at the bottom of this slide, as you can see. So I told myself, since there is a prime representational form for perfect numbers, there must also be one for amicable numbers. The main objective of this research was to provide new knowledge to the branch of number theory by explaining some of the aspects of amicable numbers that are not yet fully understood or known. Some of them are the distribution of amicable numbers and the prime factors within amicable pairs. In the case of the distribution, this includes the properties of amicable numbers in the Cartesian plane, and in the case of the prime factors, the goal was to find any patterns within the prime factors of amicable numbers in order to create a standard prime representational form for them. So my methodology was divided into two parts. The first part including the graphical analysis, and I created three graphs to look at the distribution of McCollum numbers, and for each an expected equation was created, and to measure accuracy, a ratio between the expected value and the actual value of the amicable number was calculated. For each of the graphs, I used the term big amicable numbers to refer to the larger number in the pair, and small amicable numbers for the other number in the pair. So in the case of 220 and 284, 220 will be the small one and 284 will be the big one. So first of all, the y-axis amicable graphs. For this, I created two graphs, one for big amicable pairs and the other one for small amicable pairs. So the amicable numbers were plotted on the y-axis while the x-axis went up by 1. So both of the graphs had a ratio very close to 1, meaning that the expected equation was accurate, and it followed a power-like relationship with a form of a constant of about 210 times x squared. Uh, in the case of the distribution, uh, this means that amicable numbers follow a power-like growth. So the third graph is the amicable pair function. And in this case, I graphed small amicable numbers in the x-axis and big amicable numbers in the y-axis. The expected equation also had a ratio very close to 1, and it was of the form of 1.1 times x, uh, which it confirms this power growth of amicable numbers because it is linear. And it makes sense that it's linear because when you compare a power-like growth in the x-axis versus a power-like growth in the y-axis, uh, it gives you a linear equation. Some of the limitations of the graphical analysis include that the graphs were created with 145 plots or 145 amicable pairs. And plotting more amicable pairs means that the accuracy of the results and the expected equation will be improved. So what I got out from the graphical analysis, what I found is that amicable numbers grow in a power-like form. Next is the number theory approach. In this case, all amicable numbers from 1 to 20 million were prime factorized, and I looked at the patterns within their prime factors for the creation of two conjectures regarding a standard representational form for amicable pairs. For the first pattern I found, I conjectured that all odd amicable pairs have 3 as their smallest prime factor. Uh, some of the limitations of this conjecture include that it was evaluated for amicable pairs from 1 to 20 million. And for further strength of this conjecture, it has to be evaluated for larger value amicable numbers. The other pattern I found led to my second conjecture, uh, which states that all amicable pairs can be represented in 4 main forms: 2 for all odd amicable pairs and 2 for all even amicable pairs. Some general limitations of the number theory approach include that, in the case of my second conjecture, although the standard form was narrowed to 4 possible forms, a single standard form for all amicable numbers was not achieved. Additionally, the two conjectures were tested for amicable numbers from 1 to 20 million. And testing these conjectures for greater amicable pairs will increase the strength uh, of these conjectures.